it was 12th or something. So 14th is when it is ending for the offline semester. I think we will have one on 16th. I think that should be okay. And given that you have an exam next Sunday, not having a class on Saturday is okay, I suppose. Okay, we'll do it that way. Okay, shall we start today?
Yes, sir.
Okay. Okay. So as I said, no, today's focus will be on the variational autoencoders or VAEs. Okay. So as a precursor, we were looking at latent variable models last time, correct? Now, what are latent variable models? These are models that are defined as okay. So whenever I talk of a model, yeah. So p theta, which is a distribution over the data variable, right, is what is called as a model. So wherever we talk of model, it is p theta that we talk of. Okay. Now, in a latent variable setting, that p theta is given as a marginal over the joint distribution of two variables. Okay. One is called the data variable, of course, x, which is given, and one is the latent variable that is not observed. I mean, that's why the name latent or the hidden variable. Okay. So what happens in a latent variable model? So what is a latent variable model where p theta, the model, is given as a marginal over the joint distribution of the latent and the data variable. So that is what is called as the latent variable model. Unfortunately, this does not have a pointer. Otherwise, I've been so nice that I pointed things out when I was recapping. Anyway, okay. Now, as the name suggests, the latent variable model, the latent variables are not observed, right? They are not observed. They are to be estimated together with the model parameters. So, typically, Z is also estimate or learn along with the model parameters theta. Okay. Now, the way it is defined is for every observed data point, which is in the data set D, there exists a corresponding latent variable that is not observed. Okay. So several examples, latent variable can be discrete or it can be continuous. If latent variable is discrete, the example that is given is that of the Gaussian mixture model or k-means clustering, okay, where the latent variable denotes what cluster, right, or what group of Gaussians that it belongs to. Okay, that is one example. The other example is a latent variable which is continuous, wherever you have this encoder-decoder model. It need not be auto-encoder. Any kind of encoder-decoder model is a latent variable model with the output of the encoder seen as a feature or latent variable corresponding to xi, right? So that is, yeah. So feel free to ask questions. I'm just recapping what we saw in the last class. If you have any questions, you can raise your hands and ask them. Okay. Now, this is about the definition of latent variable model. Now, the question is, how do we model distributions using latent variable model? So that is the question. So now, as I said, the p theta of x in the case of latent variable model is given as a marginal over the joint distributions. And in all latent variable models, the optimization is usually carried out by maximizing the log likelihood or minimizing the KL divergence. Okay, so the objective is to maximize the log likelihood or minimize the KL divergence. So for the rest of the lecture, right, I will be using the term maximization of log likelihood, not minimization of KL divergence, because they are equivalent. The reason I'm using the term maximization of log likelihood is because that is what is usually used in the literature everywhere. Okay. Okay, so now how do we model how do we get the parameters of latent variable model? As I told, in latent variable models, right, the latent variable also has to be estimated jointly with the model parameters theta. So now what do you mean by estimating the latent variable? Because we are talking about random variables here, and latent variable is another random variable. It amounts to estimating a distribution over the latent variable. Okay, that is what it means by estimating a latent variable. How did we do that? We wrote down the log likelihood as L theta, okay, and we multiplied and divided the log likelihood by some distribution that we would want to estimate on the latent space, okay, call it as Q of z given x. And then with the Jensen's inequality, what we found out was that there exists a lower bound, okay, on the log likelihood that we would want to optimize. So yeah, the storyline is the following, right? There is a model, latent variable model with parameters theta, and we want to estimate the parameters of that model theta along with the distribution over the latent variables, right? Now, the distribution over the latent variable is what we called as a variational latent posterior denoted by Q of z given x. Okay. Now, when you introduce this unknown latent variable or distribution over the latent variable into the model, you cannot directly optimize the log likelihood, okay? Because in most of the latent variable models, computing this integral, right, to get your p theta, okay, p theta is an integral over the joint distribution of x and z. That is not feasible because you don't know what the latent variable is. What you can do is take a guess on the latent variable distribution, which is called as q of z given x. Once you take a guess on the latent variable, distribution on the latent variable, there will be an inequality that arises, which means that you will get, see, observe this, what you would want to maximize, which is the log likelihood L theta, uh, whenever you take a guess on the latent variable, okay, via the distribution Q, there will be a lower bound that is created on the log likelihood. Okay. Now that lower bound is what is called as the evidence lower bound or ELBO. Okay. With a choice of Q and theta, you will get a particular ELBO or the evidence likelihood. Sorry, evidence lower bound. Okay. Now the goal in all latent variable models is to find out model parameters theta and a distribution over the latent variables q such that the evidence lower bound is maximized. I mean, what we actually need is to maximize the log likelihood, but because we cannot do it exactly, what we do is we will optimize a lower bound on the log likelihood, which is called the evidence lower bound. So which takes this particular form that I have written in the box item. Okay. Any questions so far? Because this is of paramount importance because this is what we are. This is the idea that we are going to use multiple times when we optimize. Like when we look at VAEs and diffusion models. All these models, right? They work in this particular principle that there is. We are looking at a latent variable model. Okay. What is a latent variable model? It is given by where the distribution over the data is given as a marginal over the joint distribution of the data variable and another unobserved variable denoted by z called the latent variable. Okay. The goal is to minimize the K divergence and find out the parameters theta. Now we cannot do it because we cannot do it because we don't know what the latent variable is. So we assume a distribution over the latent variable called, denoted by q of z given x. Once we assume a distribution over the latent variable, there will be a lower bound that will be constructed on the objective, the log likelihood that we would want to maximize, right? And when we are maximizing it, we would learn both the model parameters theta and the distribution of the latent variable by maximizing the lower bound. Okay, and that lower bound is given by this expression, right? Expectation of log of p theta x and z divided by q of z given x, and the expectation is over q of z given x. So this is what we optimize whenever we are looking at VAEs and diffusion models and so on. Any questions on this? Please ensure that you understand this like pakka, right? I mean, then after that we will continue. Yeah, Raghavendra, go on.
Yes, so this Q of Z given X is also unknown, right? So how do we compute the expectation over
I'll
that?
tell you. I'll tell you that.
Okay.
Till now we don't know what Q of C connects. That's why I said no. Look at the boxed item. It is an optimization, joint optimization over theta and Q. You have to compute both theta and Q. Okay, they are jointly estimated.
Yeah.
Right.
We'll cover that, right, sir?
Absolutely. That's exactly what we will do. Yeah. Any other question? So this broad philosophy of what we are doing is clear, I suppose. Okay. Now we took an example after that in the last class, which is a Gaussian mixture model. Gaussian mixture model is a latent variable model. Okay, it's a proper latent variable model where p theta is given by again marginal of the marginal over the joint distribution of x and z, right? And this is the definition of a GMM. No, this equation, second equation, p theta of x is given by a linear combination of multiple Gaussian distributions having different means and variances. Now, a set of parameters are the mixing coefficients, which are alpha 1 through alpha m. There are m number of mixtures, m number of means, and m number of variations. Sorry, variances. Now, what do? We want to solve that optimization problem, right, with respect to theta and q, right? How do we do it? We do it alternatively. First, we solve for theta, assuming that q is known, and then we will solve for q, assuming that theta is known. Okay. Now, what can be shown? Raghavendra, I said this last class, maybe you have forgotten. See, this is in GMM. The way to find this q, you said that q is unknown, no? What can be shown is that at a given theta, the optimal q, okay, that would make the lower bound tight. What do you mean by lower bound tight? The lower bound that we have constructed on the log likelihood will be equal to the log likelihood. That is the best value that it can assume. No, lower bound can assume the best value which is equal to the log likelihood. Now that would happen if the q, the choice of q that you have made for a given theta is p of z given x. Okay, so if q is fixed to be p of z given x or p theta of z given x, then that is the best estimate for q. Is that all right?
I mean, sir, we said that we would cover this in the TA session, but I think last session we did not have it, so maybe
No,
we'll
no.
cover this
What
in
I
the next
meant is,
session.
What I meant is, what will be covered in TA session is that
The
the proof of this, that
yes.
optimal Q for knowing a particular, I mean, for given a particular theta is p theta of z given x. Okay, now this will be covered. So this is an algebraic proof. But what is important is that I mean, see, I didn't do it in the class, and I don't want to do it in the class because in VAEs and diffusion models we will not use this because in neural models we will not know what p theta of z given x is. Okay, that's the reason. So the jump from mixture models to like autoencoders, I mean VAEs, is because of this fact. See, had we knew p theta of z given x, then the problem of latent variable models is solved because you have the EM algorithm and this can be done. But since we will not know what p theta of z given x is, that is why we need to move to something else. So please note this, everyone, that so again, I'm reiterating it. It is very, very important. So now the goal is to find model parameters theta and the variational distribution or the latent variable distribution q together, right? Now there is a result that would show that the optimal q or the optimal distribution over the latent variable is actually p theta of z given x. Okay. Now if you know how to compute p theta of z given x, then it is done. Because we know what we can do is we can do this alternative optimization where you start with a random theta, right? And set this q to be equal to p theta of z given x when we know how to compute p theta of z given x. Okay. And then with that q, you find the next best theta and keep alternating between them. Okay. Now, how do we know p theta of z given x? P theta of z given x is given by the Bayes rule, okay, which is written here. And in the case of a GMM or other mixture models, we know how to compute p theta of z given x given a particular theta. And therefore, we know how to compute q, optimal q. Understand? So once we get that optimal q, what do? That we plug in that optimal q in this evidence lower bound f theta, okay, and optimize that, take a derivative of that with respect to theta, and then find the new theta. With that new theta, you again compute p theta of z given x and keep alternating between them, which is called the expectation maximization algorithm. Does it make sense? So I have said this also, right? So yeah, so the question is, however, what if p theta of z given x cannot be computed? So if you have models And in a Gaussian mixture model or a simple other mixture model, p theta of z given x can be computed. If you cannot compute p theta of z given x, you don't know what your optimal q star is. When you do not know what the optimal q star is, how do you compute, how do you estimate the parameters of a latent variable model is the primary question that would be taken in a VAE. Does it make sense? Any questions so far? And this is exactly what we do in GMM, right? GMM is also a latent variable model. Okay, we estimate f theta, we estimate theta and q alternatively, and this algorithm is called the expectation maximization algorithm. And for EM algorithm to work, no, we need to know what the optimal q is, or we need to be able to compute p theta of z given x. Yeah, please ask questions if you have any when I am writing.
Sir, in this EM algorithm which we have mentioned, we are trying to find p theta of z given x using the Bayes theorem. So,
Yeah.
but the p theta of x given z is also unknown, right?
P theta of x given z is known, no? Because that is a single parameter Gaussian. It's actually a Gaussian distribution by assumption, by construction, by definition.
Okay.
See, I'll go back to the previous slide. I don't intend to teach GMMs anyway. So here now, yeah, that is what I have written here. Look at this.
For a given z, we have p theta of,
It's
okay.
a particular Gaussian. See, in a GMM, the way you model the distribution, I'll show that. This is how you model it. No, p theta of x is given by this linear combination of multiple Gaussians. Okay. Now this can be written this way, right? So this is equal to 1 to m p theta of z into p theta of x given z, isn't it?
Yes, sir.
Now this is alphas, okay, and this everyone is a Gaussian, okay, with a particular. Let me write this. The p theta of z is equal to some particular j, mu j, and sigma j. That's all right. So we do know that the conditional of x given a particular z is a single component Gaussian.
Understood, sir.
Yeah. Okay. Any other question on this?
So does it have to be a convex combination?
In mixture model, yeah. In mixture density is always taken convex, because the reason is, if you look at it, no, alphas are distributions over discrete variable z, isn't it? Alpha will give you a discrete, so p theta of z given j is given by alpha j, right? Which means that if we take this over all j, they should sum to 1, and all of these have to be non-zero because they are probabilities, no?
Yes.
Yeah, so they have to be, that is why it has to be convex combination. Huh? And by the way, mixture density, right? You don't, the mixture density need not be a Gaussian mixture model, no? It can be exponential mixtures or Bayesian, Bernoulli mixtures or anything. But to model data which has infinite support and the vector value Euclid, which lies in continuous space, right? Usually GMMs are preferred. Okay. And did I also talk about the clustering? See, one other thing in a latent variable model is, tell you, post training, So training is what? Post training is like estimation of theta. That's what training is all about. After we estimate theta, okay, a latent variable model can be used for two purposes. Okay, this can be any latent variable model, including a GMM. The first thing is, okay, sampling or generation, because these are generative models, right? Okay. Now, example, how do you do it in GMM is that in a GMM, okay. Now, first you sample a Z from discrete alpha 1, alpha 2 up to alpha m. So note that all of these are estimated using the EM algorithm. Once you estimate them, this is actually tossing an M phase die. So first you do that and then sample X. Okay, X given Z, okay, by Gaussian. So let's say that the outcome of this is I is the outcome, alpha I is the outcome. Okay, so let's call I is the outcome. Yeah. Once you do that, what you should do is sample an X, okay, by a Gaussian, which has the ith mean and ith variance. That's all. Yeah, that's all it is. So this is how you do a generation in a GMM. Whatever X that you get now by doing the sampling, this is Z equal to I. Okay, you do that sampling via a Gaussian. In fact, if you look at Bishop's book, which is like classical book by Bishop, pattern recognition. So what you will see is that he has shown what will happen if we do sampling. I mean, if we fit a GMM to MNIST data and do a sampling, it will look like some images, right? But it will not be like as good as it's some other generative model such as GAN. So what happens is, no, in very high dimensions, these GMMs, they often tend to have this curse of dimensionality and they will not model the data well. So that is because of the saturation of the EM algorithm. Again, I know since I'm not teaching GMM, I'm not going into details of it, but yeah, okay. This is how you sample from a GMM. I will talk about how do you sample from a variational autoencoder. But yeah, so what is more important is that one can use a latent variable model to do sampling or generation. The other thing that can be used, that these models can be used, is what is known as posterior inference. Posterior inference, okay, also known as feature extraction, feature or embedding extraction. This becomes embedding extraction if, okay, this is or it's also called as clustering if Z is discrete. Okay, now what is this? So given trained latent variable model, okay, um, and given a data point X, okay, now you just compute Q star of z given x. That's all. So this, right? See what happens is, if in the case of q, let us say it that way, compute or sample from either, both of them are possible. I'll give you, I mean, there are different variants of it. Okay, now let me tell you what it is. Compute, okay, q star of z given x or sample from it, depending upon what the case is. Okay, so what do you mean by this? Um, so given a data point x, no, post training, given a data point x, I'm finding out a distribution over the latent variable given the data point. Now let's say that let that z is discrete. Then what will happen? You take, z is discrete. If c is discrete, we have values 1 through m. So c can take m values. Z can take 1 through m values. So if you are computing q star of z given x, what will happen is there will be a discrete distribution over z. Right? There will be an entire distribution over z. What is this? This is called clustering. So every x now is divided into one of m possibilities, right? That is clustering. Okay. Now if z is continuous, then what will happen is, given a given an x, okay, so you'll find out a z given x, okay, which is a sample from q of z given x, that particular star of z given x. This will be a vector in some rk, where that is where the z lies. So this is typically referred to as the embedding. So all these BERT embeddings, etc., that you see, textual embeddings and image embeddings, etc., are nothing but samples from the posterior, the latent posterior given data. So this is one other usage of latent variable models. That is why we say that we can do clustering using GMM, right? So the GMM is a latent variable model with discrete latent space, okay? And that's why we can do clustering of it. So it is either GMM or k-means, k-means is a special case of GMM, right? All these are clustering methods. But under the hood, what is happening is that you are estimating q star of z given x. So two things can be done, right? One, you can do sampling or generation, okay, which is simply the generative task that we were looking at. The other thing that you can do is what is called as posterior inference. That is that given a particular point x, you can find out q star of z given x. Is this okay? So these
Sir,
are two tasks. Yeah.
Sir, in the embedding case, the received vector will be a one hot vector, right?
No, 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 no. I mean, you mean the x you are talking about, is it?
No, sir. The z
The,
given a, the
no,
resultant
it's not.
vector.
No, 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 no. It is not one hot. No. See, that's what I'm saying. Think of an autoencoder, right? You have an encoder-decoder model. I cover all that in detail, but I'm just giving you an overview here. So if you have I mean, if you know what BERT embeddings mean, there's a trained model. You pass it through a trained model, right? Your x, which x can be one hot, and you will get a particular vector at the output. That's all it is. That vector
Okay.
is a sample from z given x. Yeah, that's your embedding.
Okay.
So why do you call it as a sample? So that means for a given x, you can get a
The,
different values of z. Or
the reason I'm calling it as a sample is because whenever the latent variables are continuous, no, you won't get an entire distribution over z given a particular x. Especially in cases like BERT and all that. But as we will see in a VAE, right? Q is modeled. I mean, you will get an entire distribution over Z. Okay, but typically when people call it as embedding extraction, no, it's always a sample from Q, not an entire distribution. See, I just wanted to make this distinction that if Q is discrete, then given an X, you get an entire distribution over Q, sorry, Z. right? But when Q is continuous, typically, what happens is you get a sample from Q star, not an entire distribution. I just wanted to make the distinction.
Okay.
Any other question? So remember these two things, no? I mean, this is how the VAE paper starts also, that the goal is to do two things. That given data, you need to first learn a latent variable model, which is by maximizing the likelihood or ELBO. Second task is to, after you have completed your training, we need to do a generation, okay, or sampling, and then we do posterior inference. So let me write it in the next thing itself.
Sir, which paper is it? What I forgot the name you mentioned.
Are you looking at my handwritten notes at all? Just asking, because there I have, like, at the end of my every each notes, I'll tell you the name of that paper, but I encourage all of you to actually look at my handwritten notes. It's
It's
very lucidly written.
Kingma and William.
Come again?
It's a Kingma and Willing.
Yeah, Welling and Kingma's paper. I'll tell you the name. See, what's important is, don't digress. What's important is that all of you look at my handwritten notes. At the end of my handwritten notes, key papers are listed, and I expect. And by the way, for the exams, I think this is the way to make you read. Right? There is only one way. For your exams, right? All the papers that I have listed in my handwritten notes at the end of them, they are a part of syllabus. Okay, so you are supposed to read those papers. There are only 4-5 papers per topic, so please read them. Yeah. So the name of the paper is VAE's paper is auto encoding variational Bayes. If you Google for VAE original paper, you'll get that. But the title is auto encoding variational Bayes. So please read my handwritten notes once, and the citations that are given at the end of each chapter. I urge all of you to do that. Okay, so now the problem here is that given D, which is data samples drawn IID from an unknown distribution Px. Okay, the goal is threefold. One, learn a latent variable model with unknown latent posterior, right? I mean, this is what it makes different from EM. Okay, so if you read the introduction of that paper, no, they'll actually say that because P theta of z given x is unknown, we are assuming that it is not known. We want an alternative method, because otherwise, in fact, they explicitly say that EM cannot be used because we don't know what P theta of z given x is. Okay, that's the first goal. The second goal is that you need to do enable generation, sampling, post training. Third goal is to enable posterior inference. Which is nothing but estimating Q star of the units. Okay, so these are the three goals that are cited in the VAE paper, or maybe let me just show you that. It would be nice to see that once. See, a lot of times, right, we these VAE paper, these papers are sort of intimidating, but one of the goals of this, one of the goals of designing this particular course was to ensure that you people start reading papers, students start reading papers, and you don't get intimidated looking at it. Okay, so they will say the following here. Yeah. So we are interested in and propose a solution to three problems in the above scenario, right? Efficient approximate maximum likelihood estimation for parameters of theta. Let's not worry about map estimation. It's the efficient approximate maximum likelihood estimation of parameters of theta, number one. The second thing is efficient approximate posterior inference of the latent variable given an observed value x for a choice of parameters theta. For a choice of parameters theta meaning post training. Right? This is useful for coding or data representation tasks. That is what is meant by embedding extraction or representation learning. Second thing is you need to efficient approximate marginal inference of the variable x. Okay, this allows us to perform all kinds of inference tasks where a prior over x is required. Common application in computer vision include image denoising, inpainting, and super resolution. All these are generative tasks. Okay, so these are the three questions that is asked. So this is that paper, no, which is VAE's paper. We'll go into all these details and math in a while. That is what we do in this lecture. But yeah, so these are the three questions that are of interest, which is learn a latent variable model with unknown p theta of z given x. Oh, I should also show you that now that they say that EM is not feasible. Yeah, interactability. Look at this, no? The first point here in 1, 2, interactability. The case where the integral of the marginal is interactable, okay? Where the true posterior density p theta of z given x is interactable. So the EM algorithm cannot be used. Is that okay?
So it is intractable because we need to do it over all values of z, or?
Well, not necessarily, right? I mean, for instance, if you assume z to be continuous variable with unknown distribution, you cannot find that integral. One thing. The other thing is, see, observe that p theta of z given x involves a division by p theta of x, okay, which is again an integral over the joint distribution, and this integral is over z. So if you assume z to be of very high dimensions, that integral cannot also be computed.
Okay, yeah,
Okay.
got it.
Yeah, so because that is why EM cannot be used here, and we need something else other than using EM. That's the prelude. So please read. See, these are sort of seminal papers, okay, which are very good to read, and you'll gain a lot of insights. I have gained a lot of insights by reading those papers as a student. So please do read them. I recommend all of you to read that. Similarly, that FGAN paper. I don't know if I showed you that. So we covered that. No, this FGAN. Then it's variational divergence minimization. Let's see. Yeah, this one. Training generative neural samplers using variational divergence minimization. So this is what we actually covered in class. Russian author. So this was the paper that I covered in class. All these lower bounds that we constructed, etc. So with the background that you have right now, please read the paper. It's short and extremely insightful. Okay. I urge you to read all these, at least these fundamental seminal papers. Okay. Right. So we have these three objectives to learn given this data. So we'll start doing it. Okay. So now okay. Recall that in a latent variable model, p theta of x is given by the integral of p theta of x given z times p theta of z whole dc, right? So this is also equal to the joint distribution of. Okay. Now the goal is to learn theta star that would maximize the log of the likelihood, right? So we saw that this is approximately same as finding out the theta such that the lower bound on the evidence is maximized, which is the evidence lower bound where okay. Now f theta q is given by the expectation of log of p theta x and z divided by q of equals with respect to q of z given x, right? All of you with me so far? Now we need to find the theta such that it is maximized. Okay. Now let us simplify this. Q z given x log p theta of x given z times p theta of z divided by q of c given x is equal to expectation log of p theta of x given z q of c given x minus expectation c given x log of q of z given x divided by p theta of c. All right. I just used two things here. One, linearity of expectations and law of logarithms. Any questions on this step? What did I do? There is log of a b divided by c. I wrote it as log a minus log c by log b. So minus came here because I inverted the numerator and denominator. Is that all right? Hello, are you there?
Yes, sir.
Yes.
Is it all right? Any questions on this? Respond, how do I know? Maybe I'm not. This is all right, no? Yeah, okay. Okay, let's move on. So this is expectation of log of p theta of x given c, and this is with respect to u of z given x minus. What's the second term? Can you recognize the second term?
KL divergence of QZ given
Yeah,
and
this is
P2.
the KL divergence between u of z given x and p theta of c. Yeah. So this is actually the loss function of a VAE. Okay, this is thing but ELBO, right? We are writing the evidence like evidence lower bound, expressing this way. So this, see, if you want to remember something, this is something that you would want to remember. This is the conditional log likelihood. Okay, let me interpret it later. Okay, so this is the equation. So you have ELBO can be decomposed into two terms. One which is an expectation of log of p theta of z given x given z, and there is a KL divergence between q of z given x and p theta of z. Okay. Now what is done in a VAE is that, so first thing that you do is approximate
So one question.
Yeah.
For this to be KL divergence, there should be a p theta of z term also, right? Before log?
No. There should be a q of z given x term.
Yes, q of z given x.
The expectation is there, no? Expectation is integral q z given x log of q by p, isn't it?
Okay.
It is integral q z given x log of q z given x divided by, isn't it?
Yes, sir.
That's KL, no?
Yes.
Yeah. Okay. No. Okay. So what's important now is that you approximate p theta of z. Sorry, p theta of x given z. Okay. And q of z given x using neural networks. So let's call that as q phi, because there are two neural networks theta neural networks with parameters theta and phi. Okay. So what we do is, see, look at this ELBO, right? There are two distributions that we are talking about here, which is q of z given x, which is the unknown posterior. Okay. The other thing is p theta. Other thing is p theta of x given z. So we represent both of them using neural networks. Now observe the difference here from the EM algorithm, right? In EM algorithm, q of z given x, the optimal q of z given x was known to be p theta of z given x. Here, because we don't know what p theta of z given x is, we approximate that using a neural network. Now the question is, what do you mean by approximating? Okay, let me write that. What's important is question. Okay. What is meant by approximating distributions using neural networks? Approximating distributions using neural networks. Okay, it's very important. There are two ways here, right? See, one way is that there is a probabilistic way, okay? And there is a deterministic way. Okay. Now, what do you mean by a probabilistic way? Let's say that there is a neural network here. Okay. Now, this is like q phi of z given x. Okay. Now, this takes a sample of z as input. Okay. So, z, the neural networks are deterministic functions, which is that, you give a fixed input, it will give you a fixed output always, right? So now a sample of x, sorry, a sample of x it takes as an input, and what it gives out are the parameters of the distribution q of z given x. So this is typically called as the probabilistic neural network, okay, where a neural network, okay, will give you the parameters of a distribution. Now, typically, let's say, so example, if q of z given x is assumed to be, let's say, a Gaussian of some mean and variance, okay, this neural network will give you mean and variance as output. Make sense? So this is called the probabilistic way of representing a distribution using a neural network. Okay, a neural network will give you the parameters of a distribution. So note that in most of the probabilistic ways of representation, right, you assume the underlying distributional form for the distribution that you are assuming. Okay, what you make your neural network output the parameters of the distribution. So that is called the probabilistic way. Okay, so there is a deterministic way which we have already seen, right, which is should have written it the other way around, because typically in latent variable models at least, x will have a larger dimension compared to Z. Doesn't matter, but yeah, so just to ensure that it is consistent. So if you are doing it in deterministic way, let's say that you are modeling some p theta of x given z, right? Now it will take a sample of, give a sample of z, okay? It will give you, what will you give you, what will a deterministic neural network give? It will give you a sample simply give you a sample, okay, x cap from p theta of x given z. This is the deterministic way. So here the neural network is not giving you parameters of the distribution, but it is giving the samples from the distribution. So the example is a GAN generator, no? A GAN generator is a deterministic neural network. I mean, all neural networks are deterministic that way, but a GAN generator is modeling the conditional data distribution in a deterministic sense. So what do I mean by that? I mean to say that that it will give you a sample from the distribution that it is modeling, but not the parameters of it.
Sir, but for a given Z also, let's the sample X will be different, right?
No, not in a GAN. In a GAN, right? If you fix Z, you'll always get the same X, no? Because neural networks are deterministic functions. That's the whole point that I'm trying to make. See, the variability in the generated data comes because Z has randomness into it, right? Because we know that Z typically is sampled from a Gaussian distribution. That's why different Z will give you different X's. But post training, a GAN generator, or for that matter, any neural network is a fixed function, right? For a given fixed input, it will give you a fixed output. There is no stochasticity in a neural network by design. Does it make sense?
So one question. So in the probabilistic way, so we estimate only the parameters for only one distribution or a family of or a group of distributions.
Yeah. See, it is one distribution in the sense that if you are looking at q phi of z given x, right? Q phi of z given x is actually q phi of z given one particular x always, isn't it?
Yes.
These mu and sigma will be a function of x,
Okay.
right?
Yeah.
For a particular x. But if you are saying that the same neural network is being used to estimate the q phi of z given x for different values of x, then you are estimating it for a family, and that's what is happening. Because once you train given one particular x, it will give you the parameters of q phi of z given that particular x.
Yes.
Yeah. Okay. See,
Okay. It generates a family itself, right? And
right. I mean, see, for a given x, it does not generate a family.
yes, correct.
Should be clear about it. Right? When you say, see, there is no stochasticity associated with the neural network. So for a fixed x, it will give you a fixed output. Now, in the probabilistic way, what will happen is that there will be that will be seen as parameters of. In fact, how do you do it practically is that suppose mu x is let's say that like z is in some k dimensions, right? Then what we'll do is this output, this neural network will have k plus k squared dimensional output, no? Because sigma will have k squared parameters, mu will have k parameters. It will be k plus k squared stacked into a long vector. That is the output. Okay. So now for one x, it will give you one output, and that can be interpreted as the parameters of a distribution. So it is modeling a family in the sense that for every x, it will give you parameters corresponding to that.
Yeah, got it.
Yeah. So I'll ask you a question now. What do you think? What way do you think? I mean, these are the only two ways that you model that you use neural networks in any task. Okay. Here is a question. What do you think a classifier, a K-class classifier is doing? Is it a probabilistic model or a deterministic model?
Probabilistic.
Probabilistic.
Why do you think it's a probabilistic model? See,
Because
what is the classifier model, by the way? What distribution is a classifier modeling? Take a classifier, what distribution does it model? You take an X as an input. What distribution is it modeling?
Underlying
Giving you
data.
the probability of the classes.
This is what it models, right? All classifiers model p theta of y given x. Correct? In fact, the so-called cross entropy laws that you use is actually minimization of KL divergence, no? Actually, it's minimization of KL divergence between the true posterior, label posterior, okay, and the neural network model posterior. This is exactly what you do, right? When you minimize, this is cross entropy because the other term, which is the entropy term, will be independent of theta. The first term, right, which is the expectation of log of p theta of y given x with respect to p of y given x. This is what you minimize. Negative of this is what you minimize, which is the cross entropy term, which is nothing but the K divergence, right? So even a classifier is doing the same thing that they are doing, right? It is doing a maximum likelihood estimation or minimizing the K divergence. But now the output, what do you get? Do you get a sample from this distribution, or do you get the parameters of this distribution? So let's say that y is a discrete distribution that will take 1 out of k values, okay, with probabilities py1, py2 up to pyk. So post training, when you do an inference for a particular x, what do you get at the output? Do you get a sample from the p theta of y given x, or do you get parameters of p theta of y given x?
Get a sample.
Why do you say so? Do you get one of the see that depends? Okay, so here is the answer, right? The way to look at it is, so if you look at the entire classifier, so suppose you take the final layer to be the argmax of logits, okay, then it is a sample, right? But if you stop at logits, then it's actually a distribution, probabilistic way. You see that? If you take the logits, right, then it sums to one, right, and it's all non-negative. Okay, which is the softmax. So if you take the output of the softmax, which is the logits, no, even before the softmax, if you take the logits, then it's an entire distribution. Okay, you can see that as, you can interpret that as parameters. If you take the argmax, okay, take the softmax and then take the argmax of all possible values, then it becomes a sample of this discrete distribution. Anyway, so not something that I intended to say. But anyway, so these are two ways to model distributions, right? One is the probabilistic way, where the neural network gives you samples from the distribution that it is modeling, and the deterministic way, where the neural network will give you samples from the distribution that it is modeling. Okay. Now, what do we do in a VAE? Q P, right? Distribution Q phi of z given x, okay, is modeled see, there are multiple instantiations of it, okay? Okay, let me write it. Q phi of z given x is modeled probabilistically. Probabilistic. Okay, and p theta of x given z is modeled using either probabilistic or deterministic, as the case may be. Yeah, I'll tell you. These are different instantiations of same idea, right? Probabilistic or deterministic neural networks. So basically, both of them are modeled. Q phi of z given x is always modeled probabilistically. Okay, p theta of z given x can be modeled probabilistically or in a deterministic way. Okay, let us see one instantiation where you have. Okay, so now data is a set of xi's. You have n of them. They are sampled from Vx you have, right? Now typically x is in some RD. In all latent variable models, z is assumed to be in some Rk, okay, where k is much less than d. That is how it is done in latent variable models. Now, what will happen is there is a neural network. This neural network takes xi as input, one of the xi's as input, and this is modeling q phi of z given xi. Right? Now, this is, as I said, it will model probabilistically. So, in one of the instantiations of, one of the naive implementations of VAE, now Q P of z given x is assumed to be a Gaussian. Okay. It's a distribution in Z. The mean of this is mu of x because it's a function of x. The variance is a function of x. So typically it is assumed to be you can model it to be a diagonal matrix. Okay, diagonal matrix of sigma 1 through sigma k. Let us call this as sigma of x, sigma x vector. Okay. Now what will happen is that in a VAE, so this will get mu of xi as the output, or sigma of xi as the output. Okay. Now note that both ux and sigma x lie in k-dimensional spaces, right? Because I've assumed sigma x to be a diagonal matrix, they both lie in k-dimensional spaces. That means that the output of this, this will be a d dimensions. This will be 2k dimensions. Okay, this is also called the encoder network. Simply modeling QP of Z given X using neural networks. But there is another neural network. We said that we also model P theta. So this will take Zi, which is a sample from QP of Z given Xi as input, and then this will model P theta of X given Z. So now let's say that this gives you a sample. In this case, I'm assuming that this is modeled deterministically. Okay, this network is also hold on. Oh, this will take Zi, the sample from QP of the given Xi as an input. Okay, and this network is also called the decoder network. This is a VAE. Okay. Now, one thing that is to be noted here is, of course, this is k dimensional. This will be d dimensional. Okay. Now, see, one thing that is to be noted here is, I will tell you, is that there is no direct connection between the encoder and decoder networks. Okay. They are not connected at all, right? So what is happening is, given an xi, okay, so you first get the parameters of the distribution q phi of z given x. Then, having those parameters, you sample a zi from q phi of z given x, okay, and give that zi as an input to the decoder to get a sample from p theta of x given z. Here, the output of the encoder, right, does not go as an input to the decoder. Do you see that? The output of the encoder does not go as an input to the decoder. I should write that. So this means that the output of the encoder okay, doesn't go as an input to the decoder. Okay. Is the setup clear now? What is happening? Yeah, we'll have to now see how to train this, or rather how to get the parameters by optimizing the ELBO, and also we have to see how to do generation and inference later post. I mean, because you remember, no, we had these three goals that you learn a latent variable model, enable generation, and enable posterior inference. We'll see all that to be done. But in terms of like architecture, is all of you clear on what is happening?
So the input to the decoder is a sample from Q of Z given X.
Q P of Z given X, correct.
So we indirectly use it, right? Because
No, we do.
the
We
distribution.
use it. I'm not saying we don't use the encoder network. I'm saying that the output of the encoder does not go as an input to the decoder. I didn't say that we are not using the encoder. Encoder is very much used.
Okay, but it's used to only determine the parameters of the distribution. And
It is
then we
used to
sample.
determine the parameters of the distribution, and using those parameters, you sample. Okay. And once you sample, use that sample as an input to the decoder.
Yeah, got it.
Sir, I have one question.
Yeah, go on.
For QP z of x, we say that is a normal distribution on the variable z with mean mu x and sigma variance sigma x. So why this mu mean and variance are on the or on x? They should be on z, right?
No. They are, see, they are, okay. I mean that they are functions of x. See, look at this. No, I've said that both of them lie in Rk, which means that they are in D space, but they are functions of x. See, when I write
Okay.
off something, it means that they are functions. I'm talking about them being functions of x.
Okay, but they are over the z since
Absolutely.
they are also k dimension.
Absolutely.
Okay.
See, neural network is taking an xi as an input, no? That's why it's a function of x.
Got it, sir.
So I mean, I want all of you to like strictly understand this, clearly understand what's happening. Otherwise, everything that we do next will not make sense. So please ask me questions if you have on how this thing works. I mean, architecture. Yeah.
K is again a hyperparameter here, or?
K is a hyperparameter. Yes.
Sir, sorry, one query. Here, the decoder network we have found out deterministically, right?
We are not See, we have at least in this exam instantiation, I have made this deterministic because I say that it gives you a sample from P theta of x given c. Yeah.
Okay. Does it, maybe you might cover it later. You can say that. I mean, like whether it changes when you do it probabilistically. If that.
Yeah, you simply get the parameters of P theta of x given z, no? That's all.
Okay.
Instead of getting a sample from P theta of x given z, you get parameters of P theta of x given z. Then it becomes a probabilistic thing.
Got it. Then again, from that parameter, we again use that
You do
into the
sampling,
encoder.
you do sampling, but typically, right, in a naive implementation of VAE, the output of the decoder itself is taken as a sample from P theta of x given z.
Thanks.
But yeah, so later, like in the class, no, I will also give you one example where it is taken deterministically as well. But for now, let us think that it is, sorry, the probabilistic. For now, let us think that it is deterministic. Yeah.
Sure. Thank you, sir.
Lokesh?
Yeah, sir. So for a given xi, the xi cap which we get from p theta might be different, right? Because we have a sampling step in between, and
Correct.
that might lead to a
Correct.
difference in the.
Yeah, I am not even saying that you get like xi at the output of the decoder, right? Decoder will just give you a sample from p theta of x given z. I have not established any relationship between xi and xi cap yet.
Okay.
Okay, if your question is, where is that so-called quote unquote auto encoding happening here, right? We will see that. We'll see how does it come out. Okay,
Okay.
Harish?
So this sampling process of lead from Q of P, right? So is it like generally having a random sample using like a random function from that thing, or is there a specific
Yeah.
process?
You use the standard samplers. So you can suppose if you model your Q to be a Gaussian distribution, then you can use that like standard random sampler for this.
Got it. Thank you.
Okay, so is the setup clear to all of you? Now what we should do is like with this. Now the ELBO will become a function of theta and phi, which is given by the expectation of log of p theta of x given z, and this is with respect to q phi of z given x minus the scale divergence between q phi of z given x and p theta of z. Okay, this is what it is. What we should do is that, like, we should solve this, theta star and phi star is simply the is what we need, right? We need to train both of these neural networks. So how do we do that? We do it using gradient descent, right? So we need the gradient of the ELBO with respect to phi, and we need the gradient of the ELBO with respect to theta. This is what we need, right? Because finally what we do is, this is how we train the neural networks. Assuming that we are simply doing a SGD, right? First order gradient descent. Here's how we do it. So we need the gradients of the ELBO with respect to both phi and theta. Under this, I think somehow the pages are sizes are going haywire. I should not zoom out and zoom in arbitrarily, I think. Yeah, let's keep it this way. Okay. So now with this modeling choice that we have made, no, we have to ensure that we get the gradients of the lower bound with respect to phi and with respect to theta. Okay, and then we can of course use gradient descent tool to train both of these networks. Is this all right? Now, what we will do in the rest of the classes, so getting this gradient right with respect to gradient of the ELBO with respect to phi is a non-trivial thing. And you might have heard this term reparameterization, right? It is used in VAE, like so-called reparameterization. That comes into picture to calculate this gradient, that's all. So calculating this gradient with respect to calculating the gradient of ELBO with respect to the encoder parameters needs this idea called reparameterization because of a simple fact. You look at this, no? There is a sampling step that is involved, okay, which cannot be differentiated through. I will show all that, very rigorously. But the basic idea is that there is a sampling step, and the encoder and decoder are connected via the sampling step. But sampling is a non-differentiable operation. When you backpropagate, no, through chain rule, you have to backpropagate. So let's say that you start from the output of the decoder, backpropagate all the way through the input of the decoder. From there, you should go to the output of the encoder, and those two are connected via sampling. But sampling is a non-differentiable operation. So what do you do to find the gradient of the ELBO with respect to the encoder parameters is what we should look at next. Okay, that is done through this trick called reparameterization trick that I will discuss. Okay, so I think shall we take a break? 15 minutes break. It's 10:40, 10:48 now. It's a good time to stop. Yeah, Raghavendra.
Sorry, there was no question.
Oh, that's my mistake. Okay. Yeah, shall we take a break? Satya, go ahead.
Yes, sir. They can take a break. I have one question on the assignment. So you can take it over.
Maybe later after the
Yeah.
class. Yeah,
Okay.
please do ask me after the class. Okay, so now yeah, it is 10:49 in my clock. We started late today, no, 20 minutes late. So let's cut down the break. Let's get back at 11:05. Okay, in 15 minutes. Let's come back. Let's come back at 11:05 and finish the reparameterization. So don't miss the next part of the class. No, it's pretty important. Okay, see you in 15 minutes. Then. Bye. Hello? Shall we continue?
Yes, sir.
Okay. Okay. So, can you hear me now, right? Can you hear me?
Yes, sir.
Yes, sir.
Okay, thanks. Okay, so we were looking at now computing the gradients of the encoder and the decoder parameters with respect to, computing the gradients of ELBO with respect to the encoder and decoder parameters. Okay. Now, okay. So what do we? So let's take one term at a time. No, there are two terms in ELBO. So consider computing computing the gradients of ELBO with respect to P and theta. Okay. Okay. We'll consider the first term in the ELBO. Consider the first term in the ELBO. Which is the expectation of log of p theta of x given z with respect to u phi of c given x. Okay, right? Now, how does it look like? Suppose looks something like this. No, this the above like you have an expectation of okay some function. Please note that this z, what is this z here? X given z. What is this z? The z is being sampled from q phi of z given x, right? Right. So this entire thing, whatever the log of p theta of x given z is, that is also a function of phi. Do you understand that? Please let me know if you don't understand. So this is of some random variable v, okay, and the expectation is with respect to a distribution, okay, pv, and this is also a function of phi. Let's just giving you a simpler example. I think it does. Let me use a different parameter. Maybe let's call this as some psi, and we have some distribution on this random variable V. Do you agree that it looks like this? Any questions on this? Okay, let me write it down. Maybe it will be easier that way. Here, f psi of V is actually log of p theta of x given z. Okay, and then p psi of V is simply given x, V is z. Okay, and psi is phi. Is this okay? Hello, am I audible? Okay, fine.
Yes, sir.
So now what do we need is that we need the gradients of this expectation this gradient has to be with respect to the parameter side, correct? This is what we are seeking. So let us write this down. So this is equal to,
Sir, sorry to interrupt.
yeah,
Instead of going for psi, can't we straight away use the like phi? Otherwise, it will be a bit confusion.
the reason I didn't use phi was, phi has been taken as encoder parameters. I can do that. Let us keep it that way. No, I have written it down. So let us have it that way.
Okay.
This is equal to the gradient of integral with respect to V. We have p psi of V times f psi of V dV, right? This is the definition of expectation. And we can move the gradient inside because expectation is a linear operator, right? We can move the gradient inside. This will be p psi of V times psi of V, correct? dV. Now, what do we do now next? Can somebody tell me?
Chain rule.
Yeah, we use chain rule. This is the gradient of one function, okay, times p psi of V dV plus the gradient of the other function times correct. This is what it is, right? Now, what is the first term? Look at the first term, right? You have some function here and a probability distribution here. What is that? And there's an integral. What is that? This is an expectation of the gradient with respect to p psi of V. Okay. This is not an expectation. This the first term now can be approximated using 1 over n 1 through n, and you have psi of Vi, where Vi is coming from p psi of V, right? This is again law of large numbers. We know how to estimate expectations, approximate expectations, but this cannot be written as an expectation. and therefore can't be computed. Do you see this? See, this is the problem. See, when I said that you cannot differentiate through sampling, so look at what is happening. See, there is an expectation of a certain function, and that function is parameterized by some set of parameters, right? Now, the expectation is with respect to a density, okay, and that density is also parameterized by same set of parameters. Okay, so now if you want to do that, if you want to now take the gradient of such an expectation, okay, of a function that is, see, typically what happens now in most of the neural network training, you need to take the derivative of an expectation of a function with respect to set of parameters, and these will be neural network parameters. But this expectation, right, will be typically over, let's say, px, okay, where px are simply the distribution of data which is not, which has nothing to do with the model parameters, and then we approximate this expectation with respect to, I mean, using the samples that we are given, which are the true data. Now here is a case, okay, where you need to take the gradient of an expectation, okay, with respect to a density function, and that density function is also parameterized by the same set of parameters with respect to which we need the gradients. You see that? And why is that happening? If you look at it, that is happening because our encoder network is made probabilistic. No, when we make our encoder network probabilistic, okay, then the parameters that we are getting, no, of the expectation of the distribution with respect to which we are taking the expectation uh, is that the distribution also is parameterized by same set of parameters with respect to which we need the derivatives. Algebraically speaking, what happens is that if you take the gradient, you cannot express the second term that comes up in the gradient of the expectation in terms of sample averages, okay, and therefore that cannot be computed. Is this point clear to all of you? So this implies, so if you want to generalize this implies that the gradient of the first term in ELBO, which is the expectation of log of p theta of x given z with respect to q phi of z given x, okay, so can't be computed. Yeah, can't be computed directly is what it means. Can you all appreciate this fact? Any questions on this? See, this is the key part. Okay, this is where we need what we call as the reparameterization that we will see. But is this clear? Any questions on this? Hello, am I audible?
Yes, sir.
No questions? Oh, great. Now, how do we solve this? Solution called as the reparameterization trick. Okay. Now, what does this mean? Recall that we wanted the gradient of expectation of some function that is parameterized by some parameters, and the distribution was also parameterized by the same set of parameters, right? We wanted this. Now all we need to do is couldn't be computed. correct? So what you do is, if or express in terms of another distribution which is independent of right. This is exactly what is called as the reparameterization. Okay, I'll tell you. Reparameterize. So what does this mean? This means that, let's say that suppose there exists a random variable epsilon, okay, it's some distribution p epsilon. Okay, so note that this is independent of the parameters, okay, such that your v, which is the random variable of interest, is some function of this epsilon. Then the expectation of with respect to p psi of v can be shown to be equal to the expectation of f psi of, what is v now? V is equal to g times epsilon. Okay, and this expectation now will become the expectation with respect to p epsilon. It is either you take it as a homework or can be taken in the DS session just to show that these two are equivalent. Okay, this is also called the law of the unconscious statistician. Okay, abbreviated as Lotus. I mean, this is a standard probability proof. You can just do it. 2 steps you can show that. So now, what did we show? That there is this random variable v, right, with respect to which we are taking an expectation. Now we represented that random variable, okay, in terms of another random variable epsilon, okay, a function of another random variable epsilon that is independent of these parameters psi. And if you do that, then the expectation, okay, of the function with respect to this random variable p psi now will become an expectation with respect to another random variable p epsilon that is independent of the parameters psi. So this is what is called as reparameterization, right? I mean, this g function is called the reparameterization function.
So how do you find this epsilon?
Yeah, good question. Now that depends upon like in the VAE paper, no, they give multiple ways to find this epsilon, and it's not enough if you only find epsilon. You need to find g also. No? You need to find an epsilon and a g such that this happens. I'll give you examples of how to do this. Okay, at least in the case of the naive implementation of VAE, I'll tell you how this is done. Okay, so now this, if you do this, now it's easy, right? So now did we solve the problem? The problem was to find the gradient of this expectation with respect to p psi. Now this is equal to the gradient of the expectation of this can be done. No, you just now push the expectation inside the gradient inside the expectation, and that can be computed using sample averages. So now this is approximately equal to, take some m samples of epsilon, and this equal to 1 to m, and you have the gradient of f psi of G of epsilon I, where your epsilon I now is sampled from P epsilon. So now you will not have that have this uncomputable integral problem now, because the dependency, the expectation is not now with respect to P psi, but it is with respect to P epsilon. Okay. Now let us look at an example of reparameterization. Somebody asked me how to do that. So example of the is spelling correct? Reparameterization, right? Yeah. Okay. Reparameterization. Okay. In VAE, in particularly in VAE. Okay. I mean, this reparameterization is independent of VA or nothing. It's a general probabilistic technique. Okay, but yeah, I'll show you an example of VA. Okay. So let us take the same example where my Q phi of Z given X, Q phi of Z given X, okay, is a Gaussian distribution. See, and it has parameters, let's say mu of X and sigma of X. Okay, right? This is what it is. Now let us now reparameterization. Okay, so now what is phi, by the way? I'll tell you. Best way to write it is, say that this mu is a function of phi because this is the output of the neural network. Sigma is also a function of parameterized by phi, a function of X. Okay, and now that is why this becomes a function of P. Now let us reparameterize. Now let epsilon be a Gaussian distribution with zero mean and unit variance. Okay, if you do that, then Z is equal to mu phi of X plus sigma phi of X times epsilon. If I do this, then Z will now have distribution equal to Z given X. Do you agree? Now this function, right, is the G function that I'm talking about. This is G of epsilon. Now if you take a normally distributed random variable with zero mean and unit variance, excuse me, so you add it with a constant and scale it with a constant. If you do that, then the output random variable will again be Gaussian, okay, with the mean and variance given by the scale and the shift. This is reparameterization. Do you see that? Is this all right? Where this G function is simply mu plus okay. So this is one way. Okay. There is another way to reparameterize, which is not often used in VAE literature, but yeah, there is one other way to reparameterize, which is called as. This is one example. The other example that is given in that paper is what is called as the inverse CDF method. We will not use inverse CDF method, but I am simply mentioning it for the sake of completeness. See, suppose X is a random variable, okay, and f(x) of X denotes its CDF. Okay, now we know that fx of x is simply the integral of the PDF function, right, over this. Now let us represent that by some random variable z. Okay, now this is a function of, now the question is what is the distribution of z. Do you understand the question? Now given a random variable, you compute its CDF. Okay, now CDF itself becomes another random variable. Okay, question that we are asking is what will be the distribution of CDF of a random variable? Do you know that? Does anyone know that? It would be a uniform distribution between 0 and 1. So please take it as a small homework and show this. That you take any random variable, okay, and show that the distribution of its CDF of any random variable is uniform between 0 and 1. Can you already intuitively see why that should be the case? If you take the CDF, CDF is a non-decreasing function, right? And it is upper bounded by 1. So which means it is bounded between 0 and 1, right? Always the CDF. So that should be a uniform distribution between 0 and 1. This is a standard proof, okay? So please find it out in the internet or just do it as a homework, okay? Now the thing is, this implies that if I take a U that is uniform between 0 and 1, okay, and compute x to be equal to the inverse, okay, of the CDF that is evaluated at U, then the distribution of x, okay, let us call this as x cap. X cap is inverse CDF of a random variable x. Then the distribution of x cap is same as that of x. That is the idea. Makes sense, right? See, now we know that the distribution of the CDF of any random variable is uniform. Okay. Now that means that if you take a uniform random variable between 0 and 1, okay, and make a transformation, okay, using the inverse of the CDF of any random variable, then the outcome will be another random variable which would have a distribution that is same as that random variable whose CDF you have inverted. You see that? So in this case, the G function. So now epsilon is uniform 0, 1. And the G function, okay, is the inverse of the CDF. So this is another reparameterization technique which is called the inverse CDF method. Is this all right? See, but the thing is, in this case, the only requirement is that the CDF of the distribution that you are modeling using your encoder has to be invertible, right? Which is not always the case, and that's why in most of the cases in VAEs the distribution of Q is taken to be Gaussian, and this sort of reparameterization is used, which is the affine reparameterization is used, not the inverse CDF method. But I hope that you got the idea behind reparameterization, right? Let me repeat what is happening here. So we wanted to find the gradient of the encoder parameter with respect to ELBO, right? Sorry, we wanted to find the gradient of the ELBO with respect to the encoder parameters. that cannot be found out because the ELBO has an expectation of some function with respect to a distribution, and that distribution itself happens to be a function of these parameters. Okay, so we cannot compute the gradients. So what do we do about it? The way to do it is represent that distribution with respect to which you are taking the expectation in terms of another arbitrary random variable which is independent of the parameters. Okay, so that representation through a function is what is called as reparameterization. So if you do that, then this expectation can be written in terms of an expectation over that arbitrary random variable, and therefore the gradients of this function with respect to the encoder parameters can be found out. So that is the idea, and we saw two ways to do reparameterization, which is that if you assume your QP to be normally distributed with a certain mean and variance, the way to reparameterize that is start with a Gaussian random variable which has zero mean and unit variance, and scale it with the sigma, and shift it with the mu. You will get another random variable whose mean and variance is what the mean and variance of q pi is. Any questions so far? Now we will use this to compute the gradients and then backpropagate. But yeah, if you have any questions here, please ask me. This is actually one of the crux idea of VAEs, because otherwise it's simple, right? You are like maximizing the likelihood, representing the distributions using neural network and backpropagating. But what's important is once you represent a distribution using a neural network in a probabilistic sense, you have to get to reparameterization. Otherwise, you cannot compute the gradients. That is the idea. Right. Go on, Raghavendra.
So are we saying that we are transforming the distribution that we get to either a standard normal or a uniform in this case? Is that the way to see it, or?
The other way around, no? See, we are representing the output, the distribution of the encoder, okay, or distribution that is being modeled by the encoder in terms of standards normal 0.
Okay, and the transformation, I mean, is the G function basically, right?
Transformation is a G function, and that's it. That is a user-defined function. No, it is nothing to do. You're not learning it or anything. It is just a user-defined thing.
And is that also the way we say that, okay, that random sampling process we eliminate and then we introduce some kind of a determinism here?
No, there is still sampling. Sampling is happening in epsilon. I mean, we are just re-representing that in terms of some other random variable, which is not a function of the. See, it is only to do a simple thing. All we need to do is express this expectation that is there in ELBO with respect to a distribution of a random variable which is independent of the parameters. That's all. That's all we want to do.
Okay, so sampling this way still allows us to flow the gradients backwards.
I will show you how to do that.
Okay.
See, now, I mean, algebraically, you are convinced, no, that now we can express this expectation now, right?
Yes.
Basically, the distribution which is I mean, which you are sampling from is not now dependent on phi. It is you got it, no?
Yeah.
Yeah, that is the basic idea. Any other question? Okay, so now let us write what is happening. So now what happens is that you have the encoder network. Okay, the encoder network. Okay, this is not to write it as. Yeah, Karthik, go on. You had a question. No?
No, sir, sorry.
X goes as an input, and this is modeling Q pi of z given x. Okay. So what happens here is this neural network gives you mu and sigma. So what you do is sample epsilon from normal 0, 1. Okay, let's call this as xi. So given a particular sample, you take an epsilon from normal 0, 1, and then do get your zi by multiplying this with sigma phi of xi. Okay, we got this zi, correct? Now take that zi and pass it through the decoder. And get an xi cap. Okay? This is what is happening. You understood, no? So do you see the difference between these two? Here, yeah, just zoom it here. Here what we are doing is that we started from xi, got a mu and sigma, sampled zi using that mu and sigma directly from q phi and then gave that zi. Here when we reparameterize, what did we do? We got mu and sigma, okay, sampled an epsilon from an arbitrary, from standard normal 0, 1, and then got zi by reparameterizing. Is that all right? Do you note the difference now after before and after reparameterization? Yeah, I hope that you got it. So now what do we have to do is we need to compute the gradient of the expectation of log of p theta x given z with respect to q phi of z given x, correct? Right? Now this is equal to the gradient of expectation of log of p theta of x, okay, given what is z now? Z is given by this particular
G
formula.
of
Yeah, this particular formula. Let me call this as g of epsilon. Okay, and this is with respect to p epsilon. Is that all right? Strictly speaking, no, this g function is a function of p now, because look at this, right? I mean, it has mu phi and sigma phi. It's parameterized by phi. Okay. Now the question is, we got rid of the dependency on phi, right? This expectation now can be is equal to 1 over. If we sample m samples of epsilon, right, then it is equal to j through 1 through m, and we have log of p theta of x given p psi of epsilon j. Please note that for a particular xi, okay, for a given xi, we can get m number of zi's. See that? Or one x, right? Okay, m zi's can be obtained. Do you understand that? Because we are doing sampling, right? Like outside of the encoder. Since we are doing sampling, we can sample for one xi, we can sample multiple zi's. But typically, I mean, what is done in implementing VA is that they keep capital M to be 1. That means that they only do one sampling and send it across. Okay, so which means that the sum will only be on one particular sample. Hope that it is okay. So the next question is that how to compute. How to compute log of
Sir, here we are doing it in a probabilistic approach, right? For the encoder.
encoder is always probabilistic. Xi
Oh.
will give you mu and sigma. Once you get your mu and sigma, you sample epsilon from, let's call this, yeah, epsilon from epsilon j, let's call it. You sample epsilon from normal 0, 1, and then you reparameterize and get m zj's.
Okay.
This is good.
So
Yeah.
there is some like so if we write it like this, so there is some linear translation happening between the output of encoder and the input of decoder.
Yeah, input of the, yeah, that is reparameterization. No, in this particular case, that is what I'm saying. If you assume your Q to be normal, mu sigma, then this reparameterization is adaptable. There is no rule why this is the only way to reparameterize. No, that's what I'm saying. Suppose you assume your Q to be some other distribution, you just have to find an epsilon and g such that it transforms. See, what is important is that now this gradient, right? The gradient that we are computing here, this will become, this expectation will become independent of phi. That's all we need.
Correct.
And for that we do reparameterization. Now, what sort of reparameterization you do is a design choice. That depends upon what form do you assume on Q phi and what epsilon will just transform, what epsilon and G combination will transform that into this is the question. That's all. That depends upon whatever you use.
Okay, sir.
Is that all right?
Yes.
Yeah. Okay. Yeah, Sarvesh, you have a question.
So in the last step, 1 by m, so there should be a gradient inside, right?
Yeah, there's a gradient here. So this will be, thanks. Yeah, go on, Raghavendra.
So can you just repeat why that m can be taken as just 1 here?
See, it's like you are approximating this expectation by a single sample estimate. That's all. It can be anything. People take it as one and also experiment. I mean, in your assignment, I'll ask you to experiment with different values of m. Okay, but yeah. So generally, I mean, like in the most naive implementation, you just take one sample of z for one sample of x. But it is not. I mean, it's not hard and fast, right? I mean, you can make your m to be a hyperparameter and play with it. Yeah.
Yeah, because I think in this equation we say that it is an expectation, so we are free to choose the value of m here, right?
Correct.
And
A single
because
sample, and also single sample estimate is not a good way to do it. Yeah, always.
okay. Yeah, thanks.
Okay, great. Yeah. So okay.
Sir,
So
I
now
didn't
next
follow on this part, sir. Can you please explain once again?
part. See, the
Sir.
thing is, you sample for one xi goes as an input to the encoder, right? You get a mu and sigma. Now with that mu and sigma, you can sample any number of zi's, no, for a particular xi.
Yes, sir.
So that
Depending
is
upon
what
the
I have,
choice of m.
that is what I have represented as capital M. So you sample like multiple samples from. So it's like for let's say that xi is an image, no, for a given image, for one particular image, you will have m different embeddings.
Correct.
Right. So that is the, I mean, that is the sort of advantage with a probabilistic encoder, right? That unlike in a BERT, etc., where for a given text sequence of tokens, you only have exactly one embedding. Here you can have a plethora of embeddings for a given particular input because you are modeling it probabilistically, correct? Once you do that, if you have m of them, to compute the first term, right, you need to take an average. I mean, meaning you take a sample average of all those MZIs basically, right, CJs. But what I said is that some people, when they implement VA, they make this capital M to be 1. You can do it 1 also because it's a hyperparameter, but m being equal to 1 is not a great choice because you're approximating an expectation using one sample, which is not a good thing to do, no?
Okay.
Yeah, Sarvesh.
Sir, this x, so p theta of x given z. So this x is all x's, right? x1, x2, xn, because of we have to maximize the likelihood of all x1 to xn
See,
being
but
the.
but we are doing the entire treatment for one particular data point now. See, whatever we are doing now, there is an outer sum on all data points. You take a batch size and do it over batches.
Yes.
But I'm doing it for only one xi now. For now, I'm only doing it for one x. So this is actually xi. And I should not be writing it as xi because it's a distribution over a random variable, right? But what I mean to say is that only one sample is what we are doing it for. which should be extended to the entire data set on a batch level.
Which is so like it's
I was
stochastic.
going to
Like,
yeah,
Okay.
or yeah, stochastic when you do it at the batch level, because it's usual training. No, I'm telling you how to train for one sample. You can train it sample by sample or take a batch and do it. Doesn't matter. But we'll see that. I was going to say that at the end of the lecture, but this is only when all that we are doing it is for only one data point. Okay.
Okay. Thank you.
Okay. Now the next question is, any other questions on this? If not, we'll move on. Now we have to compute this log of p theta of x given z. No, how do we compute log of p theta of x given z is the question. So again, there are multiple ways to do it. Okay. So now one way to do it is that express using some parametric distribution. Okay. Now, for example, this is not the only way to do it. Again, for example, like assume p theta of x given z to be coming from a Gaussian distribution. Okay, what is the distribution on x, of course, and you assume the mean, okay, to be equal to the output of the decoder. Okay, the variance to be equal to identity. So note that in this case, I am representing the neural network, right, the decoder network probabilistically. Okay, now where d theta of z is the, okay, let us call that as x cap. We have been calling it as x cap, no? X cap, which is d theta of z, is the output of the neural network of decoder. Okay, now in this case, what happens is that this xi cap that we get, no, which is d theta of zj, right? Okay. Now this we are interpreting this as the mean of a Gaussian distribution, right, of p theta of x given z. So in this case, let's see what happens to log of p theta of x given z. What is this equal to? This is equal to that term, no, 1 by 2 pi t by 2 sigma inverse. It is identity. It will go away. This will be e power this is for the point xi, no, x, okay, let's call it as x minus, what is the mean? The mean is given by the t theta of z. The identity matrix is the variance, no, this is equal to this. Okay, now ignoring the constant, let's just say some 1 by 2 pi. Write it as proportional because the other terms are independent. Proportional to log and e power will go away. This will be x minus. Now you see where the auto encoding thing is coming from. No? It will become a squared error loss, okay, between the input data point xi and the output of the decoder. If you assume your p theta of x given z to be Gaussian, so which implies now the expectation of, what do we have? Expectation of log of p theta of x given z, this with respect to q p of z given x. This is what we wanted, right? This we saw to be equal to the expectation is with respect to p epsilon. You have log of p theta of x given g of epsilon. Okay. Now sample in terms of sample averages, how do we approximate this? Is approximately equal to 1 by m. So if you sample this under the assumption of Gaussianity, there's a minus here, is equal to xi minus d theta of where e1 through zj are equal to, let's say zj is equal to mu phi of xi plus epsilon j times sigma phi of xi for j equal to 1 to m. See, now you don't see the dependence on phi here, so maybe I should write it that way. Hold on. Yeah. Can you see that there is a dependence on z here? This entire thing, this thing is a function of phi. So do you see the dependence on phi? It depends on phi through z, correct? Because z is dependent on phi, correct? This is what it is. So now what we should do is that, now how do we do like one training of encoder? One iteration of encoder is as follows. I'll write that now. You have xi as an input. This is the Q phi network. This will give you mu phi of xi and sigma phi of xi. Okay. So take these two, sample epsilon j from normal 0 1, okay, and find out zj as mu phi of xi plus epsilon j times sigma phi of xi, okay, and then take this zj and pass it through the decoder. Modeling p theta of x given z, and this will give you d theta x cap I, or rather x cap j, which is d theta of zj. Okay. Now what do you do? Like there is a forward pass. This is the forward pass, right? Take this, get this done, and take the. Okay. So get your z. Okay. From your z, get it through this. This is one forward pass. Okay. Now how do we do reverse pass? Reverse pass is compute. So for one particular xi, you need to compute 1 by m. You note that for a particular input xi, you have multiple possible outputs because you have multiple embeddings, right, with different m's. You compute this, okay, and then take the compute the gradient of this with respect to p, okay, and then simply backpropagate this all the way to the input of this. What happens here, by the way, once it comes to the input of the decoder? What will happen? So you have to take this gradients and backpropagate through this operation now, zj operation, right? This
That
operation,
means
and then
we'll also have to remember this EJ that was used here, right?
of course, you have to say that for all m's. No, you have to remember that zj. So, okay, so maybe I will write it this way to make it easier. From here, it'll go like this. Okay, first it will come like this. And from here, you travel like this. This is for the reverse pass. So now forward pass also, it comes like this, and through this, okay? And then from here, you go like this, okay? And oh, sorry, I think I changed the color. Hold on. This is the color. You come like this, okay? And from here, go like this, yeah? So once you get this, then you pass like this. This is the forward pass and this is the reverse pass. Forward propagation, and this is the
So all this while we don't change theta, right? We keep the theta fixed.
yeah, we keep the theta constant. To hold on, I think. Okay, so I'll have to do it this way. Oh, to ensure that what I'm writing is more legible. Hold on. This is only for training the encoder, not decoder. This thing, there is this, there's an epsilon. Okay. The note that I'll write it. Note that gradients do not flow through sampling. Do you see that? So maybe I'll write it in a different color, easier that way. This is sampling. That's it. So this is like one iteration of training the encoder with the first term. We have not looked at the second term yet. This is only for the first term. The first term for the encoder by keeping the theta constant. Any questions on this? I see a hand raised, Harish.
Sir, we get m gradients while back propagating, right? For each
What?
DJ.
Sorry, I didn't follow. Can you repeat? It was obscure.
Sorry. So we get m gradients, right? While since we have
one gradient. No, one gradient. See, what happens is you take m of z's, right? You pass all those through the decoder, and you get m x j caps, correct?
yes.
So you compute this entire thing, this thing, right? You take the difference with each of them individually and sum them off. So that will be one scalar. That will be one scalar.
Got it. Okay. So we are
Not-
summing up it at the end.
Not one m. So it is like m different outputs. You take the difference between them and you sum, and then it will be one scalar that you backpropagate.
Got it. Okay. Thank you, sir.
Any other question? See, your second assignment will have this to be implemented. So yeah, I think this should be clear. So let me know if you have any other questions on this.
Sir, why do we need to get a scalar sum at the decoder output? Like we have m different xj's, and we can like compute the log.
See, No, no. See, look at what is doing. So we should not deviate from math. So what is happening is we need to compute the expectation of q phi of z given x for a particular x, for one x. Okay. We represented that in terms of an expectation over another random variable. So expectation has to be computed and back propagated. You understand? So you have to compute the expectation of sample averages at the output of the decoder, and you get one scalar that would be back propagated.
Expectation of the sample averages and okay.
Isn't it? So this is, look at this equation. No? This equation is what we are trying to back propagate, isn't it? That's the first term in ELBO. So this is for a given x. So for a given x, you need to compute the expectation of that log likelihood with respect to q phi of z given x for a particular x. And that we represented as an expectation over epsilon, okay, which is a sum over all m samples. So we have to pass all those to the decoder, compute this, and then take a scalar and then back propagate. Okay.
Okay.
You can
So
actually
there
make
was
m to
a
be.
so there was a second term for ELBO, right? I mean that does not contribute.
See this one thing at a time. I'm only doing it. See, look at what we are doing. Don't forget what we are doing. Look at this. All this is for the first term, the gradient of the encoder parameters with respect to the first term. There's a story for the second term and both of the terms for the decoder. We have to still come one thing at a time.
So this is not the complete gradient that we flow back.
We are not, no, we have not
Yeah,
completed
sure.
the training.
Sorry, sir.
It's only the first term, that to the encoder parameters, right? So if you have questions, see, this is the most complicated thing. The rest are actually easy. It's just simply training a neural network. This is the most, that's why I took the most complicated thing the first, and then we will go one thing at a time. Okay. Any other questions on this? If not, let's move on. So now this the second, now we have to compute the gradients of encoder for the second term. Okay. So what is the second term? The second term is the scale divergence between q phi of z given x and p theta of z. Okay. Now what is done is p theta of z is assumed to be normal 0 1. Okay. See, note that this is assumed to be independent of theta. This is a model assumption that is made, and there are lots of other improvisations over VAE that would question this and make it dependent on theta also. Okay, so for the naive implementation, this is made independent, assumed to be Gaussian 0 1, and it is made assumed to be independent of theta. So in that case, what happens is we have q phi of z given x, okay, to be a Gaussian of mu and sigma, right? Right. Now this implies that the second term, which is the scale between this will be equal to scale between two Gaussians. Okay, one is a Gaussian another is a Gaussian 0 1. Okay, so this is what is this? The deterministic form for this. Okay. Given by, let me just tell you what it is. Huh? equal to half log this determinant of this minus d plus the trace of sigma inverse of x, or I can write it as minus half log of this and so this plus mu phi norm mu phi of x squared. This is what it is. You can show this Gaussian between two KL between two Gaussian distributions can be deterministically found out. You can simply take it as a small homework and do this. Okay. Yeah, this is what it is. Okay, so KL now is simply a function of sigma vx and mu x. So this means that this encoder decoder thing, write it again. Xi we have q p of.
Sir, is it square of norm or just the norm?
I think it should be square here. Yeah. Mu phi of xi, you have sigma phi of xi, right? All you need to do is just one forward pass to get your mu phi and sigma phi, right? And let's write this as some KL, which is a function of mu phi of xi and sigma phi of xi, right? So now you have to compute, yeah, one forward pass, and for the reverse pass, you just have to compute. Don't even have to go to decoder at all. Just compute this KL of mu xi, comma sigma phi of xi, okay, and then simply take the gradient, of course, no. Then simply back propagate it here. What happens is, no, for one iteration of encoder training, you will have like one gradient coming through the decoder, okay, and like there will be this plus the KL gradient also gets added here, huh? Okay, we'll have to add both the gradients here. So this, what we are adding here, okay, this will get added with the gradient that is coming from the decoder, and this completes the encoder training. Is that all right? I think they should be straightforward, no, nothing complicated here. Now to train the decoder, how do we train the decoder? So first thing to be seen is the second term KL term is independent of decoder parameters theta, right? We don't have to use that at all. Now what should we do is that we just take an xi to have q phi of z given x. We just finish this and then close the class. This is sigma phi of xi, okay? Then you have like epsilon j coming from normal 0, 1. Then you compute zj to be right, and then you pass it through the decoder. Goes in. What you get is xj cap, right? Now how do we train this? So we have to do one complete forward pass as usual. then you do sampling, and once you do from here, it goes like this, and then it goes like this, goes like this. You have to simply compute the gradient theta, which term you have to compute? The term is xi minus d theta of zj. Compute the gradient of this term with respect to j, right? And then simply back propagate this all the way to the input. That's all. This is one decoder trying. One iteration of decoder trying. All right. Easy, right? That's all. So now we are done with the training of VAE. Okay. In the next class, no, when we begin, we will look at how to do inference, which is we have to do sampling and also posterior inference. No, I think it's obvious, right? I mean, you can, once the training is done, you just discard the encoder and pass it through pass a Z through the decoder. You will simply get the generation, and you take an Xi, pass it through the encoder, you get the embeddings, right? That's all it is. Always remember, right? Whenever we are doing sampling in an encoder-decoder model, generation is always done through the decoder model. Okay, and the embeddings are extracted through the encoder model. So we will continue from here. So what I will do in the next class is that we will look at like complete the VAE discussions and also look at 1-2 improvisations over it. So especially I want to talk about one state-of-the-art VAE model called vector quantized VAE or VQ VAE, which is what is used in stable diffusion and all that. Okay, that would be like 30% of the next class. And next we will go to diffusion models, which are the state-of-the-art for like image generation these days. Okay, which is actually one particular form of the VAE. But I urge all of you to kindly go through my notes and also today's discussion on VAEs and how to train them. I think I'm sorry I actually did it this way, right? I mean, I inadvertently zoomed it at this point, but yeah, I think you can also zoom it, right? Because it is convenient. So please go through the class notes and also my handwritten notes and read the VAE paper and be thorough with all this before coming to the next class, so that it will be easier for studying diffusion models and so on. Okay.
Sir, one question.
Okay. Yes.
So the first KL term that will be used to update both the encoder as well as decoder, right? Like in the same pass.
No, hold on. There is no first term is not the KL term. The second term is the KL term. See, you just said first KL term. There is no.
Sorry. I mean in the overall equation, the first term.
The reconstruction term it is called. Okay, the reconstruction term is used to update both encoder and decoder. But when you are training the encoder, you keep the decoder parameters fixed and vice versa.
So can't we so does that mean in one pass we cannot update encoder and decoder simultaneously?
How do you do it? No, see, you have to take two gradient passes. I wrote the equation also right here. Here, yeah, this is how you do it. First you have an encoder update and then a decoder update.
Okay.
Right. So when you train the encoder, you keep the decoder parameters fixed and vice versa.
Okay.
Yeah. Arijit?
I had a question on the assignment. Is this the right time to ask?
Yeah, let me just any questions on the class before we go to the assignments?
Yeah, so I had one question. So for example, during this training, right? I mean, we start with the decoder training first or the encoder training first? I mean, in practical implementing.
Doesn't matter. You just train one pass of encoder, one pass of decoder. That finishes one training. Yeah.
And any thoughts on the convergence? I mean, how well this converges compared to say GAN?
Yeah, this will very nicely converge. There is no adversarial training that is happening here, no?
Yes.
Unlike in a GAN, there is no min-max. There is no, I mean, encoder is not adversary to the decoder, right? They are both working towards the same objective.
Okay.
VAs are known to converge much better than GANs. Yeah, because there is no adversarial saddle point problem. There is no saddle point problem here. Yeah.
Yeah, understood. Thank you.
Okay. Yeah. Questions on assignment, you said. Yeah. Go on.
Yeah. So, sir, as I understood it, maybe I'm wrong.
Can
1
you
and 2
go?
we are doing with.
Sorry, can you make it quick? I have another class at 12:30, so
Yeah,
make
yeah,
it quick.
sure. So 1 and 2 anyway we are doing with butterfly and rest all the animal data set, right? So anyway we have to retrain the model with animal. So for the butterfly one, can we go with our independence or freedom, like choosing our loss and etc. Right? Because anyway we are doing all this condition like usual loss, WGAN loss
Arijit,
separately for.
Arijit, hold on. What is your precise question? Please ask me your precise question. I didn't understand the question.
Okay, then let me do one thing. Let me WhatsApp you. Okay, that would be better. I think you have a class now.
No, it's okay. You can ask me the question. I still have 5 minutes. You ask me the.
Okay, no, I mean
point.
to say, yeah. So the butterfly dataset one, which we are doing 1 and 2, I can use any loss of my choice, right? I mean, for example, WGAN or all. There is no boundation there. Only the conditions are applied for the animal dataset, which again, anyway, we have to retrain the model. Am I right?
Again, what is your question here? So
no,
question
I
will
mean to
have.
say, butterfly one, we have the freedom to use any loss function or anything, right?
GAN, you always use one loss function, right? Which is that saddle point
Yes, yes.
problem. What is the other loss function that you would use?
Because no, because there is I mean, we can use BC loss, etc. Right? Also.
For a DC GAN, loss does not change. Only the architecture changes, no?
Yes, right.
Are you asking whether you can use an MLP for butterfly? Is that what the question is?
Yes, kind of.
So yeah, you can use anything. See, but again, that's why I'm asking you that please, if you make your question precise, the answer can be given precisely.
Okay, I think I will ask you separately then. I mean,
Okay, think about it and let's ping me
yes,
on WhatsApp. Yeah, thanks.
yes,
Yeah,
sure. Thanks. Bye.
Sanjit.
Sir, just to confirm, next week we are not having a class and also we won't be having a quiz, right? Like every alternate
Yeah,
week we were supposed to have a quiz.
correct. So the schedule will change. So the quiz will be the week next afterwards. Correct.
Okay, sir.
See, on that note, no, like happy Dasara to all of you. Yeah,
Thank you, sir.
Satya,
Same to
go
you.
on. Yeah.
So I have two questions in assignment. One is that we have mentioned is the decoder network for the 8th and 9th question, right? So we discussed the decoder network only in the VAE. So it's a similar concept we have to use it in the Beyond as well?
Yeah, yes, correct. So I've precisely told you what to do, right? You train another network. See, when you are training the GAN, just have another network which will take the generated image and just gives back the input noise. And you can take an MSE between them and train it together. Okay. Along
Okay,
with
okay. And one,
the along with the adversarial objective.
okay. I think that's the same follow-up question on 12th, I guess. So yeah, we mentioned that use the augmented images for the training, right? So is it only augmented image we got to use, or we have the existing original and augmented together we got to pass it together?
Whenever you are taking augmented images, you should always take the original plus augmented. You should not give away the original thing. Original images rotated by 2-3 angles, right? And that would be your data set will increase by 3-4 times. Yeah. Okay.
Sorry, so one more thing. So this you mentioned the two inputs to be used, right, in this latent space. So it is same distribution or it's a different distribution? It's the two inputs you mentioned.
What two
Two input
inputs?
vectors. As a fifth question, randomly sampling two input vectors. So it should
Yeah,
be
just same distribution, right? I mean, in a GAN,
same
when you
distribution.
sample, you only sample from the same distribution at the input. Otherwise, if you sample from two
Okay.
different distributions, you'll yeah.
Okay. So it's a Z only we are using. We have to do the two times. We have to take the two input. Okay.
Take two Zs, pass it through the encoder generator, and then interpolate between them and observe what happens at the output. Okay.
Okay. Thank you, sir.
Yeah, Karthik.
Sir, about the exam, so portions till this time, including the references that you have mentioned in your handwritten notes and all the classes. That's what we should be
Correct.
expecting, right?
Correct.
And like it would be a theory only, and mostly derivations would be involved. Just want to know the type of queries that we should be more prepared.
I have not set the question paper yet. So it'll involve some math. Okay. I'll not be asking you questions like differentiate between GANs and VAEs. That's not how it will be. It will be like some thought provoking, and you have to practice math. Okay.
Sure. Thank you.
Yeah. It will not be descriptive. I'll not be asking you to like describe how GAN works and all that. No, definitely not. Okay.
Sure. Thank you.
Okay, so see, feel free to like ping on that WhatsApp group or Teams and get in touch with TAs. They are helpful as well. Both Suhas and Chandan, you can get in touch with them. Okay, and you can always ask me questions as well. Yeah, and all the best for your exam. I will give you detailed instructions on how the exam would be and all that once I complete the question paper, which is like I'll do it the mid next week, and once I do that, I'll tell you like what the instructions are and so on. Okay.
So,
But yeah, anytime you can. Yeah.
Yeah, sorry, sir. Should we be like looking into the previous year model paper if you have any, like whatever the paper you have?
Don't know where it is. It should be there somewhere. I don't know where it's where is it. Don't worry, yeah, don't worry too much. It's fine. Yeah.
Thank you, sir.
Okay. See you then. All the best.
Thank you, sir.
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 Have a nice week. Bye.